Alright, chemistry class, hello again, and in this video we are going to be talking about oxidation reduction reactions, or sometimes called reduction oxidation reactions, or sometimes just abbreviated as redox reactions. And I'll explain what that means. Here's how we get that abbreviation, redox, by the way. Reduction, and I'll explain what that is. Reduction, RED, and oxidation, OX. And so sometimes we'll just abbreviate it as redox. Redox reactions is the same thing as oxidation reduction or reduction oxidation. Okay? And these are a type of reaction that we're going to talk about. Remember in a previous chapter way back at the beginning of this course, we looked at different types of reactions. And this is one of the reactions that we kind of put off until later, until now, because we're going to talk about it in the context of electrochemistry, galvanic cells, voltaic cells, batteries. This is where a lot of redox reactions occur, and it's a very neat application. So let me explain first of all a redox reaction. So the first thing you need to know for a redox reaction is there is going to be a transfer of electrons. Okay? So there's going to be a transfer of electrons from one particular element to another element. So we talked about transfer of electrons when we talked about ionic bonds, and that would be two elements coming together, a metal and a nonmetal, bonding together to make an ionic compound. Here we have it happening in a reaction where there's something in one of the reactants that is going to transfer electrons to something else that is going to end up being the other reactant. So reactants, separate compounds, are going to react in a way where electrons are transferred from one to the other and creating new products. Okay? So a redox reaction is when there is a transfer of electrons. There has to be a transfer of electrons. So how do we keep track of these electrons? It'd be nice if we kept track of these electrons somehow, if we had some system to try to keep track of electrons and then be able to note whether there was a transfer of electrons from something to something else. Okay? By the way, a redox reaction, there's two parts. There has to be the reduction part and there has to be the oxidation part. So one of them is where the electrons are lost, and the other one is where the electrons are gained. Okay? So I'm just going to give that to you right now, and I'll show you how that plays out later on. All right? So you need to know that reduction is the part where electrons are gained. Okay? And then oxidation is going to be the other half of the reaction where electrons are lost. Okay? So something has to gain electrons, something has to lose electrons. One cannot happen with the other, without the other. Okay? That's why they are called oxidation reduction. They go together, or as I said, redox reactions. You can't just have something lose electrons and then nothing pick them up. You have to have both happening together. Okay? As I said, it'd be nice if we could figure out how to track these electrons, how to kind of assign maybe a value so that we can see if that value goes up or down, and that would denote whether we have the transfer of electrons, whether something is gaining electrons and something else is losing those electrons. Well, we have such a system. That system is called assigning oxidation states or oxidation numbers. Okay? And it's simply an arbitrary, somewhat arbitrary system that is devised in order to assign kind of a number that tells us the state in which it is before and after a redox reaction. Okay? So the rules for assigning these oxidation states are summarized in this table below, and we'll talk about it. And you don't need to memorize the table. I'll give it to you. You can use it anytime you need to on a test or a quiz, so you just need to become familiar with it. Okay? So let's talk a little bit about these rules for assigning oxidation numbers. And again, I emphasize these rules are simply a devised method to try to track electrons. That's what we're doing. We're just trying to track these electrons and keep track of them to see if the oxidation number changed up or down. And therefore we'd know whether electrons were gained or lost. Okay? All right. Here's rule number one, and I'll show you how this plays out in a little bit. It'll make a little more sense. Here's rule number one. The oxidation number for any pure element, just an element by itself, any element off of the periodic table. It's not an ion, it's just an element, just that symbol is always going to be 0. Okay, so if you just see Na, that's sodium, right off the periodic table, its oxidation number that we assign it is 0. Okay, rule number two. The oxidation number for a monatomic ion. That means monatomic means just one atom, but it's an ion. So it's a charged atom, positive or negative. Well, it's going to be equal to the charge on that particular ion. So if you see Cl negative, that's the chloride ion, its oxidation number is going to be -1. Okay, -1. The same as the charge right there. All right. If you saw Na plus, that's different than Na. Na by itself is a neutral atom. Its oxidation number is 0. But if you saw Na plus, that's a monatomic ion. Monatomic, just one atom. And that oxidation number then would be the same as the charge right there, which would be a +1. Okay? Number 3. The more electronegative element is assigned the number equal to the charge it would have if it were an ion. Well, this is going to play out when we figure this out later on, so I'm not going to go into this one too much because it's a little confusing. I'm just going to let this show itself later on when we actually do some examples. Okay? Number 4, the oxidation number of fluorine in a compound is always -1. So if you see fluorine, and if it's in a compound with something else, the oxidation number that you always assign fluorine, because it likes electrons, so we're going to give it a -1. Okay, we're going to assume that it likes to pull in electrons towards itself. So -1 for fluorine always. All right. Number 5, oxygen has an oxidation number of -2. So oxygen right here, each oxygen in that compound is going to have an oxidation number of -2. There are some exceptions. Okay. And the exceptions are written here, unless it is combined with fluorine or is in a peroxide, okay? But those exceptions, they won't come up very frequently. Let's just assume that oxygen is always -2, okay? -2. And number 6, hydrogen's oxidation state is almost always +1. So if you see hydrogen in a compound, its oxidation state is +1, all right? Unless it is combined with a metal. So in this example right here, you'll see that hydrogen is combined with a metal, and that's when it's going to be a -1. I know it's a little confusing, but it's there written for you, and you can always refer to it. If you see hydrogen, you just refer to rule number 6. Number 7, and in compounds, group 1 and 2 elements and aluminum have oxidation numbers of 1, 2, and 3 respectively. So if you see an element in a compound and it's in group 1 on the periodic table, it has an oxidation number of 1. Group 2 elements in compounds have an oxidation number of 2. And aluminum, oxidation number of 3. Okay? So here you see calcium right there. Calcium in this compound, calcium is in group 2. We assign it oxidation number of 2. 8. This is a very important rule. Actually, 8 and 9 kind of go together. All right? The sum of the oxidation numbers of all the atoms in a neutral compound is 0. In other words, the oxidation number of calcium plus the oxidation number of carbon plus the oxidation number of the 3 oxygens have to add up to 0. Okay? And that allows us to find the oxidation number, say, of carbon, which we're not sure, because we know calcium, we know oxygen, and then we know all of these have to add up to 0, so we can find the oxidation number of carbon. In a like manner, the sum of the oxidation numbers of all the atoms in a ion, in a polyatomic ion, have to add up to that charge. So here we have, I'll rewrite this, H2PO4, negative. Now there's a charge. Up here with the calcium carbonate, there was no charge here, so they all had to add up to 0. Now all these oxidation numbers have to add up to -1. They're all going to add up to -1. So the 2 hydrogens, the phosphorus, the 4 oxygens, all their oxidation numbers are going to add up to -1. And that would allow us to find then the phosphorus because we know the hydrogen and the oxygen oxidation numbers. Okay? All right, let me show you how this works and how this plays out. I'm going to give you a couple examples here, and I'll show you exactly how we can find the oxidation numbers. Again, the reason we're finding these oxidation numbers is to track electrons. Okay? Okay, I think what we'll do is we're just going to look at the compound here in Rule 8 and the compound here in Rule 9, and I'll show you how we can find the oxidation numbers for each of the elements in the compound. So let's look at calcium carbonate right here, CaCO3. I have to refer to my rules above. Calcium, according to Rule 7 right here, calcium is in group 2. So it has to have a oxidation number of +2. So right below calcium, I'm going to put a +2. All right? Carbon, I'm not sure. I'm going to hold off on carbon. But I do know that oxygen, according to Rule 5, oxygen has an oxidation number of -2. So that means each oxygen, there are 3 of them. I'm going to put a -2, a -2, and another -2. There are 3 oxygens. Each of those have an oxidation number of -2. Okay? Now, it's the carbon that I don't know. That's my question mark. But I do know that all these oxidation numbers have to add up to what? 0, because this is a neutral compound. There's no charge on this compound. So these all have to add up to 0. So here's all I do. I take the 1 calcium plus the 1 carbon plus the 3 oxygens, and they have to add up to 0. Okay? So my calcium, there's just 1 calcium, and that has an oxidation number of +2. My carbon I don't know, and my 3 oxygens each are -2. And all I'm going to do is I'm going to solve for carbon here. So a little algebra. So I figure this out here that I've got 2 and -6. So carbon, this 2 plus the -6 gives me -4. I'm going to add 4 to both sides. So this carbon has to be a +4. Okay? And that's what they showed up here in our example. They were able to find carbon to be 4 because they know the calcium, we know the oxygen, and we were able to find the carbon because they all have to add up to 0. Okay? Let's look here at this one, H2PO4. This is phosphoric acid, and we're able to find hydrogen. If we look up here in rule number 6, hydrogen is a +1. Hydrogen's a +1. And there are 2 of them, so +1, +1. Each of them are +1. The phosphorus, I do not know. Oxygen is a -2, and there are 4 of them. -2, -2, -2, and -2. Now this time they all have to add up to what? The charge. There's a charge on this compound. It's -1. So we've got 2 hydrogens, 1 phosphorus, and 4 oxygens all have to add up to -1. My 2 hydrogens are each +1. My phosphorus, I don't know. My oxygen is a -2. I just solved this for the phosphorus oxidation number. Okay, so this is 2, -8. Oops, sorry. This is a plus, and this is going to be -8 plus 2 gives me -6. I add 6 to the other side, and I end up getting the oxidation number of phosphorus is 5. Okay? Now remember why we're doing this. We're assigning oxidation numbers using these rules, and then we look to see if there's been a change. Has there been a change in its oxidation number from the reactant side to the product side? So we're going to track like phosphorus, for example. The phosphorus oxidation number on one side might be a particular number, like 5, and then on the other side of the reaction it might be different. Then we know that it either gained or lost electrons. Same thing here. Maybe this carbon, on one side of the reaction its oxidation number is 4, and then on the other side it's something different. And so we know that it either lost or gained electrons, depending on whether the oxidation number goes up or down. So we're just tracking the oxidation numbers to see if there's a change. And if there's a change, then we know that we have a redox reaction because of a transfer of electrons. Okay? So, as I mentioned, there are two parts to these redox reactions. One part, very important here, the oxidation part is when electrons are lost. Okay? Electrons are lost. And there's an easy way to remember that. If you take oxidation, the O from oxidation, okay, and then I, I'm going to use I for something, and then L, oil spells oil. So this is oxidation is losing. That's what that little acronym means there. O for oxidation, the I for is, and then L for losing. So oxidation is losing. Oil. Likewise, the other one, reduction, reduction is gaining. Okay, so R for reduction, I for is, and gaining G, and that's rig. So if you remember oil, rig, it's kind of a helpful little two-word mnemonic device. So oil rig helps you figure out which is which. Oxidation is losing and reduction is gaining, and that means electrons. Okay? So if you see a reaction, and here we have one, we have a reaction right here, something in this reaction is going to lose electrons and something else is going to gain electrons. Well, we can kind of break it apart into those two half reactions. Half of it is gaining, that's reduction. Half of it is losing, that's oxidation. So let's break it apart into those two halves so we can identify what is happening here. Okay? And here's how we do that. Watch. I first assign oxidation numbers. So here is sodium, all by itself. All by itself means it has an oxidation number of 0. Here is chlorine. It's all by itself. It's not in a compound, so its oxidation number is 0 as well. Now I come over here, and in a compound, sodium is in group 1, so it has an oxidation number of +1. Chlorine must have an oxidation number of -1 because they have to add up to 0. There's no charge on this. There's no charge at all. So did the oxidation numbers change? Yes. Sodium went from 0 to +1, and chlorine went from 0 to -1. So from one side to the other side, the oxidation numbers changed. That indicates we have a redox reaction. Well, who gained and who lost? Good question. So sodium went from 0 to +1. How does it increase its oxidation number? How does it become more positive? It had to lose electrons. So the sodium here is the one that lost electrons. It lost 1 electron. The chlorine went from 0 to -1, so it gained electrons. It became more negative. Electrons are negatively charged. So let's break this apart into two half reactions. Let's just look at the sodium, just the sodium. The sodium is going from Na, and over here in the compound, it has an oxidation number +1. So it must have lost 1 electron. 1 electron. It went from 0 to +1. Its oxidation number went down by 1 because it lost that 1 electron. Whereas the chlorine, you'll notice, went from 0 to -1. Okay? So it must have lost one electron, but there are two chlorines here. It's Cl2. Okay, so each of them are losing one electron. And that's why you need two sodiums up here to provide those two electrons to balance it. Okay, but the idea here is that it's going from 0 to -1, so each chlorine atom is gaining one electron because it's the sodium that lost it, the chlorine atoms are picking them up. Okay, how do we know that? It went from 0 down to -1. How does it become more negative? By gaining negative electrons. Okay, gaining negative electrons. So here we have the half reaction. This is the oxidation half reaction. This is the oxidation. And here we have the reduction half reaction. They can't happen one without the other, okay? But we're just kind of separating them so we can kind of isolate who's gaining and who's losing electrons, okay? So let's just quickly look at these right here. And we can quickly identify whether these half reactions, these are only half reactions, this is only half of the overall reaction, whether it is identifying an oxidation half reaction or a reduction half reaction. Well, let's look at A. Now there's a really easy way to do this. If the electrons are on the reactant side, obviously they're gaining electrons. Okay, they're gaining electrons, so that would be reduction. Okay, but I also want us to look at the oxidation numbers. But we'll quickly assign these just by looking at where the electrons are. Here, the electrons are being added to bromine, so that's reduction. It's gaining. Here, the iron is losing those electrons. It's on the product side, so that is oxidation. Here, copper is gaining electrons, so that is reduction. And D, the iron is gaining electrons, that is reduction as well. Reduction is called reduction because the oxidation number is being reduced. It's being reduced. If you gain electrons, the oxidation number goes down. It's reduced. So we can look at it that way as well. Look at bromine, it goes from 0 to -1. The oxidation number went down, that's reduction. Iron went from 0 up to plus 2. If the oxidation number goes up, that's oxidation. Here, copper, oxidation number goes from 2 down to 0, that's a reduction. Here again, iron from +3 down to +2, that's reduction. It's just that simple. Okay? Now, as I mentioned, oxidation and reduction reactions always happen together. They can't happen one without the other. They always happen together. Okay? So, any chemical process, here's a key point right here. You've got to know this. Very key, very key. Any chemical process in which electrons undergo changes where elements undergo changes in oxidation numbers is a redox reaction, oxidation reduction reaction, also called a redox reaction. Okay? So when there's a change in oxidation numbers, we know there's a redox reaction. Why? Because there's been a transfer of electrons. Okay? And a redox reaction is always two half reactions together. There are two half reactions together. One half of the reaction is something losing electrons. The other half of the reaction is something gaining electrons. Okay? So let's look at this example right here. Here we have a reaction, but this is only half of it. This is half of the reaction. It is copper. Look at copper's oxidation number. It goes from 0, because here copper's all by itself, and it turns into copper ion +2. So that has an oxidation number the same as the charge. How did that happen? It went from 0 to 2 because it lost 2 electrons. It went from 0 down to 2. It lost 2 electrons. That's the oxidation half reaction. In this reaction here, it does. I know you'll notice that it has hydrogen here, but the charge in hydrogen is not going to change. Let's just check this out for a second. Over here, the H plus is a oxidation number of +1 because it's the same as the charge. But over on this side, in water, hydrogen still has an oxidation number of +1. It didn't change. The hydrogen is not involved in the transfer of electrons. What is? Well, and neither is the oxygen, by the way. Oxygen on this side is a -2. It's still a -2. It's still a -2. What is being reduced? It is the nitrogen. The nitrogen's oxidation number is going from +5 on one side to +4 on the other side. Its oxidation number went down. It went down. So it went down by 1. It lost 1 electron, but you'll notice there's 2 here. It's doubled. So there are actually 2 total electrons that are lost because there's 2 total electrons that are gained. Okay? Or sorry, 2 that are lost from the copper, 2 that are gained from the nitrogen. Okay, to the nitrogen. When we put these two together, these two half reactions, then we get the total reaction right there. So we just add everything together, okay, and we end up getting all the reactants. We're just bringing them all together on one side, all the products on the other side, and you'll notice that we have to have the same number of electrons lost as gained. That has to happen, okay, and that helps us balance the redox reaction, and then we can have all the reactants combined together from the 2 half reactions and all the products combined together from the 2 half reactions. This would be the final redox reaction. But sometimes it helps us just to look at the half reactions and isolate those two, and then we can identify who is being oxidized and who is being reduced. We can figure it out from here as well. Okay, we can figure it out from the total redox reaction because we see that the copper, once we assign these oxidation numbers, it's the copper that is whose oxidation number is going up, so that's the oxidation, and it is the nitrogen whose oxidation number is going down, so that's the reduction. Okay, the copper is losing electrons, the nitrogen is gaining electrons. All right. Okay. By the way, if nothing changes, if we identify the oxidation numbers and nothing changes, that means it's not a redox reaction. Okay? So you'll notice down here, right here, if we assign all the oxidation numbers according to our rules from earlier, and notice that nothing changes its oxidation number. Hydrogen is still a +1 from one side to the other, oxygen still a -2, sulfur still a +4. This is not a redox reaction. Okay? Not. Okay. Number 3 here, is this a redox reaction? Well, after we've assigned the oxidation numbers, and let's just go ahead and do this really quickly. Let's just verify these oxidation numbers. Sodium, this is an ion, a +1 ion, so the oxidation number is the same as the charge. This is a chloride ion, so the oxidation number is the same as the charge right there. Silver ion, oxidation number is the same as the charge. Here we have the nitrate ion, and we know oxygen is always a -2, so -2, -2, -2. Why did I put it 3 times? Because there are 3 oxygens there. Nitrogen, I'm not sure, but I do know that all these oxidation numbers in this polyatomic ion have to add up to the charge right there of -1. So nitrogen plus the 3 oxygens, each are -2, have to add up to -1, and that gives me my oxidation number for nitrogen of +5. Okay? Sodium again, ion is a +1. Here we have a compound, a polyatomic ion actually, and again you'll notice that it's exactly the same as over here. So the oxidation numbers are going to be the same. Okay? Silver and chloride. Chloride here is going to be a -1. It's just like fluorine usually, okay? That may not be written in our rules, but chlorine is in group 17. It's usually a -1. That makes silver a +1 because they have to add up to 0. Do any of these oxidation numbers change? Sodium goes from +1, it's still +1. Chlorine, -1, it's still -1. Silver, +1, it's still +1. Nitrogen, still +5. Oxygen is still -2. No change in oxidation numbers. This is not a redox reaction. there is no transfer of electrons during this reaction. None. Okay? What about this one? Is there a transfer of electrons? Yes, obviously. Here is hydrogen element all by itself, 0 oxidation number. Chlorine, 0. But in a compound, hydrogen is a +1 according to our rules. That makes chlorine a -1 because they have to add up to 0. Hydrogen goes from 0 to +1. Chlorine goes from 0 to -1. Definitely each of them change, and this is a redox reaction. What is being reduced? Well, just look at the numbers. It's going from 0 to -1. It's being reduced. So the chlorine is reduced and the hydrogen is oxidized. Okay? Hydrogen's number is going up, chlorine's number is going down. That tells you what is being reduced and what is oxidized. So the chlorine is losing electrons, the hydrogen is gaining. Okay? Oops, I'm sorry. I made a mistake there. It is the chlorine that is gaining. I'm sorry, my fault. I apologize there. The chlorine is gaining. I'm sorry. The chlorine is, its number is going more negative, so it's going to gain negative electrons. The hydrogen is oxidized. It is going to lose electrons. My apologies. Okay? The hydrogen is becoming more positive, so it's losing electrons. Okay? Just remember, I forgot, oil rig. That's very helpful. Okay? Oxidation is losing, reduction is gaining. Okay? Reduction is gaining, oxidation is losing. Sorry about that. Okay. Let's practice a few of these. Okay? And we're going to just do 2 of these. We may not be able to do all of them. I can make another video or share another video where lots of these are done for you. Okay? Well, let's just choose one of these here, and yeah, let's just go ahead and do this one. Okay? All right. Let's assign oxidation numbers. Well, potassium is in group 1, so it's going to be a +1. Oxygen is always a -2. There are 3 of them, and that allows me to find nitrogen. So this is basically going to be potassium is a +1. The nitrogen I don't know. The 3 oxygens each are -2, and this all has to add up to 0. This is a neutral compound. And so that's going to give me nitrogen has to be what? This is -6 + 1, -5, so it's got to be 5. Nitrogen's got to be a 5 here. Okay? Over on the other side, this oxygen here is all by itself. It's just an element, so its oxidation number is 0. All right? And here in this compound, again, potassium is a +1. Oxygen in a compound is -2. There are 2 of them. This time I can find the nitrogen by using a similar formula. Potassium is a +1. The nitrogen here I don't know yet. And the oxygens, there are 2 of them. So 2 times -2 gives me 0. Why? Because it's a neutral compound. This time, nitrogen here has to be a 3. All right, 1 and -4 is -3, so nitrogen's got to be a +3. So yes, there's been a change here. Okay, so we can identify this and say it is the nitrogen whose oxidation number went down. It was reduced, gained electrons. How many? Well, it looks like it went down by 2, so probably gained 2 electrons. Okay, and that means each nitrogen gained 2 electrons. And then what is being, it's the oxygen. No, not this oxygen. There's an oxygen here there are oxygens whose oxidation numbers don't change, but there's at least one oxygen whose oxidation numbers did change. It went from -2 to 0. So that is a oxidation. Oxidation, it lost electrons because the oxidation number became more positive. Okay, so we're able to identify that the nitrogen was reduced, the oxygen, one of these oxygens was oxidized, and yes, this is a redox reaction. Okay? All right. I'm going to pause there, and I'll share another video with you that goes through a lot more reactions like this to identify the oxidation number and identify who's being reduced and who's being oxidized. Okay? All right, we're going to pause there, and we'll pick it up in the next video.